Hello everyone.
We
Are Team Hi everyone. Today we're going to talk about the mean value theorem. But before that, I'm going to explain the Rolle's theorem. So, mean value theorem and Rolle's theorem are almost the same. They have the same condition, and in Rolle's theorem, the function should be continuous on the closed interval a to b and differentiable on open interval a to b. So the function a and function b should be equal, so it should be continuous. And if these three conditions are met, you can get the number of c, where f prime of c is equal to 0. So here is an example of f prime of c, where the tangent line is, the slope of the tangent line is equal to 0. So, as I mentioned earlier, fa equals to fb, so f and a should have a same value of y. So here you can see that a has same value as b, they have same y value, and here's an example. F of x equals x squared minus 3x plus 2, close interval 0, 3. So if you plug in 0 and 3, you'll get same value, 2. And since the condition has been met, you can get the number c. So first you're gonna derive the original value, x squared minus 3x plus 2. So 2x minus 3. So the first derivative of x squared is 2x, and the derivative of 3x is negative 3. And since this is a constant, it is 0. So just change the x to c and equate it to 0. So you move the transpose the 3 to the left side, so it will be positive 3, and divide both sides by 2 to cancel the 2. So you get 3 half. So your number c is 3 half. Okay. Tapos na? As I mentioned before from Rolle's theorem, they have the same idea. If these conditions are met, the function of closed interval AB must be continuous and the function of open interval AB must be differentiable. And so if these are met, you can get the f prime of c, or the formula for the secant line. And here's the formula: f of b minus f of a over b minus a. So here's a graph which shows the tangent and the secant line. Secant line is a line that touches 2 points, while tangent line is a line that touches only 1 point. So this formula is same expression as the formula of the slope. And when you get the f prime of c, you can get the number of c which shows the point where the secant line and the tangent line are parallel to each other. Here's an example of the mean value theorem. To find the number c, we use this formula. So this is the example: x squared plus 4x plus 5, the closed interval 0, 4. So what we're gonna do is plug in the values of 0 and 4 to the formula. 4 and 0, divide ba. So this is your a and this is your b, the 4. And to make it more simple, cancel the denominator 4. So times both sides by 4. So 4 cancel, and multiply 4 to 2x plus 4. So 8x plus 16. And so you will get 8x plus 16 equals 16 plus 16. Here you're going to transpose 16 to the other side to leave x on the left side. After that, divide the x by 8, So x equals 16 divided 8 over 8. So the x or your number c is equal to 2.
Hey guys, for our next subtopic before we can sketch algebraic and transcendental curves, it is all about increasing and decreasing function. So how can we know if it's increasing or decreasing? So as stated in the board, if the graph is going upward, then the function is increasing. Therefore, the first derivative is positive. So now if the graph is going downward, like this, then the function is decreasing. Therefore, the first derivative should be negative. Here are some examples. In this function, x squared minus 3x plus 1. So in order for us to find where this function is increasing and decreasing, we have to first find the first derivative of this function, then equate it to 0. Let's begin. So, the derivative of x squared is 2x minus the derivative of 3x is 3. Since 1 is a constant, the derivative of 1 is 0. After finding the first derivative, we now then equate it to 0. We transfer negative 3 to the left side. So it becomes positive. Then divide both sides by 2. So we can cancel the 2 from the 2x. So we have our critical point, x equals 3 over 2. Now that we've got our critical point, which is 3/2 that we've got from our first derivative function, let's make a sign chart and put the critical point in the middle. Now let's pick a number that is greater than and less than 3/2 for us to determine where the function is increasing and decreasing. Let's say 4. So we plug in 4. 2 times 4 is equals to 8. 8 minus 3 is 5. Since it's positive, so the x greater than 3/2 is positive, we can write positive here. Now let's pick a number that's less than 3/2. Let's say 0. So plug it in. 2 times 0 is 0, and so the answer is negative 3. Since the x less than 3/2 is negative, we can put negative here. Now, for us to write the interval, let's put on the right side positive infinity and on the left side negative infinity. Now we can say that the function is increasing from 3/2 to positive infinity, and we can say that the function is decreasing from negative infinity to 3/2.
Hello. So today our next topic will be the local extreme values. So in many problems in economics, engineering, and physics, it is important to determine how large or how small a certain quantity can be. If the problem admits a mathematical formulation, it is easier to solve the problem by finding the maximum or minimum value of some function. So, suppose that f is our function and the c is the interior point of the domain. F is said to be local maximum at c provided that f of c is greater than or equal to f of x for all x sufficiently close to c. And the function f is said to have a local minimum provided that f of c is less than or equal to f of x for all x sufficiently close to f. the local maxima and minima of f comprise of the local extreme values of f. So here we have an illustration of what I have just discussed in the previous slide. So if you look carefully in this case, we see that the figure suggests that local maximum and minimum occurs only at points where tangent line is horizontal, or which f prime of c is 0, or where there is no tangent line, f prime of c does not exist. Yes, this is indeed the case. So suppose that c is an interior point of the domain f. If f has a local maximum or local minimum c, then f prime of c is equal to 0, or it does not exist. So what makes it impossible for a local maximum or local minimum to occur at c is that if we suppose that f has a local extreme value at c, and then let's suppose that f prime of c exists, if f of c is greater than 0, or f prime of c is less than 0, then what I just said earlier, wherein f has a local maximum or local minimum at c, and f does not exist, there must be points x sub 1 and x sub 2, where this point should be close to c, for which f x sub 1 is less than f of c less than f x sub 2. This is what makes it impossible for local maximum and local minimum to occur at c. Therefore, if f of c exists, it must have a value of 0. The only other possible way is that f of c does not exist. So in our local extreme values, we also need to determine the critical point. And to determine the critical point, these are the interior points of c of the domain of f, for which f prime of c is equal to 0, or does not exist. And in this case, these are called the critical points for f. Here we have an example, and this is to help us illustrate the techniques in finding the local maxima and minima. In each case, we'll have, the first step is to find the critical point. And we already know how to find the critical point. It is to derive the function. So to derive this, 3 minus x squared. The derivative of this function would be, since 3 is a constant, we will not be deriving that. And we have negative x squared. So we will be having negative 2x as our derivative. And we have found our critical point, which is derived from our function. The critical point negative 2x, which is the derivative, exists everywhere since f prime of x is equal to 0 at x equal to 0. The number 0 is the only critical point, where if f of 0 is equal to 3 as the local maximum. So here we have found our local maximum. Here is an illustration of our function f of x is equal to 3 minus x squared, where our critical point would be the derivative of this function, which is 2x, negative 2x. And our local maximum would be f of 0 is equal to 3, 0 squared is equal to 3. And here is our local maximum. So here is an illustration of the local Here's an illustration where you can see the local maximum of the function.
So now we will be solving the absolute maxima and absolute minima. In solving absolute maxima and minima, we have 3 steps. The first step is find the critical points. Second step is calculate f of A, f of C1, f of C2, and f of V. The third step is denote the greatest of the numbers as absolute maximum value of f and the least of the numbers as absolute minimum value. So here we have example number 1, f of x is equals to 1 plus 4x squared minus 1/2 x to the power of 4, as x has the range or interval of from -1 to +3. So for solving the derivative of this equation is 0 plus 4 times 2x minus 1/2 multiplied by 4x and cube. That's it. So f of x, derivative of f of x is equals to 8x minus 2x cubed. So here, this is our derivative and we can factor it out as, or 8x minus 2x cubed is also equals to 2x times 4 minus x squared. We can still factor this out as 2x times 2 minus x times 2 plus x. So here, we were given a range from -1 to +3 at which our derivative will be equal to 0 or does not exist. So here's our sign chart, ranges from -1 to +3. So we are to find a number at which our derivative will be equal to 0. So we'll think of a number ranges from 0 to 3. So let's try 2. So plug it in. F prime of 2 is equals to 8 times 2 minus 2 times 2 quantity 2. So 8 times 2 equals 16 minus 2 times 2 equals to 4 cube is equals to 16. 16 minus 16 equals 0. So f prime of 2 is equals to 0. We'll think of I will try also the number 0, which f prime of 0 is equals to 8 times 0 minus 2 times 0 cube. So 8 times 0, 0 minus 2 times 0 cube, 0, then 0. F prime of 0, 0. So our x's will be x is equals to 2 and x equals to 0. Which means if x is equals to 2, our derivative will be equal to 0 and also x equals to 0, our derivative will be equal to 0. So from the original equation, we have these numbers. Then we use these numbers and plug it in the x's from the original equation. So 1 plus 4 times negative 1 squared minus 1 half negative 1 to the power 4 equals to, so 1 plus 4 times 0 squared minus 1 half and 0 to the power 4, 1 plus 4 times 2 to the power 2 minus 1 half times 2 to the power 4. 1 plus 4 times 3 squared minus 1 half times 3 to the power of 4. So f of negative 1 is equals to 9 over 2. So for the f of 0, we have positive 1. For the f of 2, we have positive 9. And lastly, the f of 3 has the value of negative 7 halves. Now, to sketch our graph, we will be using these values. First is, when x is equals to negative 1, our y is 9 over half. So, first one is 2. Second is, if our x is equals to 0, our y is equals to 1. Then if x is equals to 2, our y is equals to 9. And lastly, if our x is equals to 3, our y is equals to negative 7 halves. So let's graph it. From the endpoint maximum value down to the local minimum value. From here, then up to the local maximum value. Then lastly, down to our endpoint minimum value. So that's it. That's our graph.
Our topic for today is optimization. Optimization is the application of differentiation, or people might know this as the application of minima and maxima. So there are three categories of optimization. The first is abstract. In abstract, we deal with equations like x squared plus 2x plus 1. The main point of this is we want to know the values of x and what is the relation of x to other numbers. The next is geometric. In geometric problems, we deal with shapes like rectangle and triangle. And we want to know what is the maximum area and the minimum area for each shape. The last is rates. In rates or rates problem, we deal with in this case, related rates or dy over dt or dx over dt, we deal with the real life situation problems. For example, when you pour a water in a specific object, you want to know how fast or how slow the water moves into an object. And The importance of these three will help us identify or solve real problems, especially in the fields of physics, mathematics, and engineering. So in our previous discussion, we've discussed the formal definition of optimization and its three categories. So our topic for today is how to solve optimization problems. So there are some guide or some helpful tips to solve optimization problems. So the first is we sketch or draw the figure if possible. Next is we get the equation or equations. And to make things easier, we must only have one variable. For example, you've seen in your equation you have x and y. You must only have one equation, like you must only have x or y. Number three, identify whether minimum or maximum. So we need to identify whether the quantity of the problem is maximizing or minimizing. This can interchange, like how fast or how slow, or how long or how short. It really depends on the problem. Number four, we derive the equation and we simplify. After that, once we derive and simplify, we apply the units based on the given problem.
So for our next subtopic, we're going to find our asymptote. So before we'll go further into that, let us first discover what are asymptotes. So a useful aid in sketching the graph of a function is to find if there is any asymptote of its graph. So there are types of asymptote. We have the vertical asymptote, horizontal asymptote, the slant, and the oblique. So we're not going to discuss more about the slant and oblique, and we'll be more focusing on the vertical asymptote and the horizontal asymptote. So here is an example. So we have this example right here, y is equals to 1 over x minus 3. So in order for us to find the vertical asymptote, all we need to do is to equate the denominator to 0. So x minus 3 is equals to 0. We transfer the negative 3 to the other side. So we can say that the equation of the vertical asymptote of this function is x is equals to 3. Now, to find the horizontal asymptote, we need to first determine if the function is top-heavy, same, or bottom-heavy. We can say that it is bottom-heavy since the degree of the denominator is higher than that of the numerator. See, as you can see, x has a degree of 1, while at the numerator there are no x variables. So we can say that y is equals to 0. So now let's graph our points. There you go. Now we're going to graph our given point. So we have x is equals to 3, our vertical asymptote, which is right here. And we have our horizontal asymptote, which is y is equals to 0, or simply our x-axis. Now, for the vertical asymptote, to determine if the graph is above or below, we're going to have to pick a number that's greater than our given value, which is 3, to determine if it's above or below. So let's say 4. Now we're going to plug in number 4 right here. So 4 minus 3 is 1, so our answer, our y is equals to 1. So we plug in right here. So we can say that our graph on our vertical asymptote on the right side is on the above. Here. Now for the left side, we're going to have to pick a value that is less than our x, which is 3. So let's say 2. So we plug in 2. So as you can see, so 2 minus 3, negative 1, 1 over negative 1 is negative 1. So we're going to plot it in. 2 and negative 1. So we can say that on the left side of our function is downward. So that is our graph. So now we're going to find our domain range. So the domain is simply all the possible values that can be plugged into our x variable that can not make our equation to 0. So we have our lowest value, negative infinity, and our highest value, which is positive infinity. So we can write here, domain is equals to negative infinity, 3 union 3 negative infinity. So for our range is actually the same. So any given possible value that cannot be equated to 0. So negative infinity to 0, union 0 to positive infinity. That is all. Thank you.
To summarize everything that we have learned in sketching algebraic and transcendental curve, we know that in curve sketching, we need to get the domain, the intercept, x, y, symmetry, asymptotes, intervals of increase, decrease, local max, min, concavity, and points of inflection. And lastly, after getting all the data, you need to sketch it. So first, get the domain. In getting the domain, we need to set the denominator equal to 0. And we know that x squared, the value that makes the denominator equal to 0 is 0. So now we know the domain. From negative infinity to 0, union 0 to positive infinity. And from negative infinity to 1, it is the domain. And from 1 to positive infinity, it is also the domain, except the value 0, because 0 makes the function equal to 0. Now that we have the domain, next thing we need to do is get the x and y intercept. So in getting x and y intercept, for getting the x-intercept, you need to equate the y to 0. To get the y-intercept, you need to equate x to 0. And since in the domain, 0 is not included, so we cannot get, there is no y-intercept. And to get x-intercept, we need to equate y to 0. So from this function, 0 is equal to x minus 1. So to equate this function, to make a fraction 0, we need to make the numerator 0. So the value that makes the negative 1 to 0 is positive 1. So we have the x-intercept 1. In getting the symmetry, we need to plug in a negative value in the function. So if the result is positive, then it has symmetry at the y-axis. And if we plug in negative x and the result is also becomes negative, so the symmetry is at the origin. The difference between the y symmetry and no origin, the graph should look like this. So this has the y symmetry, and a function that has no symmetry will only be a straight line. So from our equation, if we plug in negative x, we'll get negative x minus 1 and negative x squared. And as you can see, the values change. So there is no symmetry. Usually, a rational function has a vertical asymptote. And here, when you get the asymptote, all you need to do is equate the denominator to 0. So y is equal to 0 minus 1, and the denominator is 0 squared. So you'll get negative 1 and 0. And when the numerator is not 0, so there is a asymptote. So at x equals 0, there is a vertical asymptote. Now we move to the fifth step, getting the intervals of increase and decrease. So in getting the intervals of increase and decrease, all you need to do is first find the first derivative of the first function. So x minus 1 over x squared. So if you derive this, you need to use quotient rule. So x squared times 1 minus x minus 1 times 2x over x squared to the power of 2. So you need to combine like terms, x squared minus 2x squared plus 2x over x squared. And here, again, we combine like terms from x squared minus 2x is x squared plus 2x and x squared. Here, you need to factor it out. So you move the x to the outside and cancel the x and the denominator x to the power of 4. So the values that will be left is 2 minus x over x cubed. So you need to find a value that makes the numerator and the denominator equal to 0. So the values that make the numerator equal to 0 is positive 2, and the value that makes the denominator equal to 0 is 0. So now that we know that x is equal to 2 and x is equal to 0, we make a line chart to know if the sign is increasing or decreasing. Now that we know the x is 2 and 0, we need to make a sign chart. So just place the 0 and the 2 and find a value that is greater than 2 to know that what sign is to the right. So number here is greater than 2 is 3. So 2 minus 3 over 3 squared is negative 1, 9. So the answer is negative. So to the right it is negative. And if we plug in a number that is between 0 and 2, it is 1. So 2 minus 1 to the power of 3 is equal to 1 over 1. So the value is positive. So positive. Again, from the derivative value I function, you need to plug in again a value that is lesser than 0. So 2 minus negative 1 over negative 1 cubed. So negative 1 times negative 1, it makes positive 1. So 2 plus 1 is 3, and negative 1 to the power of 3 is still negative. So the answer is negative. And we know that if it is negative, the flow is going down, and when it is positive, it is going up and going down. From the line chart, it is increasing from, we know now that it is increasing from 0 to 2, and it is decreasing from negative infinity to 0, and also it is decreasing from 2 to positive infinity. So now that we have the increase and decrease, all we need to do to get the local max is plug the value 2 to the original function. So you're going to plug in the value 2. So y minus 2 minus 1 2 square is 1 over 4. So now we have the local max. So 2, 1/4. That is getting the concavity and points of inflection. And in getting concavity and points of inflection, you need to get the second derivative. And here you get the second derivative, and what you need to do is equate the numerator and denominator equal to 0. So in the numerator, what makes the numerator equal to 0 is 3, positive 3. And in the denominator is 0. So you're going to make a sign chart and put the values 0 and 3. And you're going to choose a value that is greater than 3 to know if the right side is concaving up or concaving down. So value 4, example, 2 4 minus 3, 4 to the power of 4. And we know the answer is positive. So here it is concaving up, positive. Next, you need to choose a value that is in between 0 and 3. So example 2. So 2 times 2 minus 3 over 2 to the power of 4. We know that 2 minus 3 is negative 1 and times 2 is negative 2. And negative divided by the positive is negative. So the answer is negative. So it is concaving down. Next, you're going to choose a number again that is lesser than 0 to know if it is concaving on the left side. So example, negative 1. So 2 times negative 1 minus 3 over negative 1 to the power of 4. And negative 1 minus 3 is negative 4. And negative 4 times 2 is negative 8. And negative number is positive. So here it is concaving up. Next, after getting the line of the sign chart, you're going to find the inflection point. It is the point where the curve sign changes. So in getting the inflection point, you need to use the first original equation. So y minus x minus 1 over x squared. Plug in the value. You cannot plug in the x equal to 0 because at x equal to 0, it is undefined. So you're going to plug in 3. So equals 3 minus 1 over 3 squared. So at 3 minus 1 over 3 squared, the answer is The answer is 2 over 9. So this is the inflection point. Now that we have gathered all these data, we need to graph it. So we know the x-intercept is at 1. And we have a vertical asymptote and a horizontal asymptote. So, and the inflection point is at 3 to 2 over 9. So it is about right here. And the local max is at 2, 1/4. So about here. And since there are no other intercept, x-intercept. So the curve should be below the x, and since there's horizontal asymptote, it will not go over the x-axis. So and all you need to do to graph this curve, just plug in a number that is lesser than 0, because since, as what I said, that there is no other x-intercept, so the graph should be below. And to get from the data, we know that from 0 to 3 is concave down. So, and from 0, so now that we have gathered all the data, first we will just plug all the data. So we know that we have a horizontal asymptote and a vertical asymptote, and we're going to plug in the x-intercept 1. So here, this is the x-intercept 1. Plug in the local max, so at 2, 1/4, so about here, and the 3, 2, 9, so about here. So if we plug in a value that is lesser than 0, so example negative 3, so it will only be approaching, going down and going to the right, since there is the horizontal and vertical asymptotes. And here from the data, from 0 to negative infinity, it is going up. So it is going up here. So this is the 3, 9. This is the intercept 1, and this is the 2, 1/4, the local max. And from 0 to 3, it said it is going down. So here it is going down, and from 3 to positive infinity, it is going up again. So it will be approaching to the horizontal asymptote. It will be only approaching because there is a horizontal asymptote. So this is a rough sketch of the function x minus 1 over x squared.